Diffusers are everywhere in modern automotive design. You'll see them as aftermarket parts, integrated into high-performance road cars like the Porsche GT3 RS, and as core aerodynamic devices on race cars, from GT3 and endurance prototypes all the way to Formula One. But despite how common they are, most people misunderstand what a diffuser actually does. When people hear diffuser, they imagine a device that somehow pushes air up to push the car down. But that's not how the physics actually works. A diffuser isn't a lever pushing air. It's a pressure management device that makes the underbody work far more efficiently than it would otherwise. Today, we're going to strip away the myths and explain precisely how diffusers generate downforce and why they're one of the most powerful aerodynamic systems on any performance car. A diffuser is a shaped section of the car's underbody at the rear that transitions the high-speed airflow beneath the floor into the slower airflow behind the car. It's essentially an expansion chamber, but not in the same sense as a closed duct diffuser you'd see in industrial applications. In motorsport diffusers, air flows under a flat floor and enters a region that increases in cross-sectional area, allowing that flow to expand while being guided back to ambient conditions. To understand what a diffuser does, we need to revisit one of the core ideas of aerodynamics, the relationship between velocity and pressure. Air moving under the car accelerates because the underbody acts like a constricted passage. That acceleration lowers the local pressure under the car compared to the static pressure above it. This pressure difference is what generates downforce. A diffuser that allows this fast-moving, low-pressure air to decelerate gradually back toward ambient pressure without causing separation. This process is called pressure recovery. In a diffuser, volume increases downstream, which by conservation of mass means velocity must decrease. When velocity decreases in the presence of surrounding flow, static pressure rises. That's pressure recovery. It's the careful control of this transition that makes the underbody more efficient, and it lets the low-pressure field under the car expand without generating huge drag or separation. The diffuser doesn't create downforce in isolation. What it does is extend and enhance the low-pressure region initiated ahead of it under the car. By managing how the fast underbody flow returns to ambient conditions, the diffuser lowers the static pressure under the car relative to the surrounding air. That pressure difference, higher above and lower below, produces a net downward force on the vehicle's chassis. Another way to look at it is this. A flat floor alone can only accelerate airflow so much before it transitions abruptly into the wake behind the car. The diffuser provides a controlled expansion path that lets that airflow decelerate in a less turbulent way, preserving the low pressure longer and reducing flow separation. This makes the whole underbody a more effective low pressure generator than the floor alone. But diffusers have limits. If the angle of expansion is too steep, flow separation can occur along the diffuser surface. In an ideal diffuser, the gradual increase in area allows the air to decelerate and recover pressure without detaching from the surface. Motorsport regulations and practical design often require diffuser angles that exceed what a simple two-dimensional duct would allow. This works because, under a car, the flow isn't isolated. It's strongly affected by the presence of the ground and vortices which help re-energize the boundary layer. To take advantage of this, diffusers are rarely left as a single open expansion. Instead, vertical strakes are used to actively manage the flow as it slows and expands. These strakes divide the diffuser into multiple narrower channels, reducing the effective expansion angle seen by the flow in each section. At the same time, strong longitudinal vortices form along the strake edges, pulling higher energy air from the diffuser core down toward the surface and feeding momentum back into the boundary layer. This continuous re-energization helps the flow remain attached even as pressure rises aggressively through the diffuser. But even with those three-dimensional effects, diffuser performance still collapses when separation dominates. Diffusers don't live in isolation. Their effectiveness depends on the quality of flow entering them. Turbulent wake from wheels, suspension, and other underbody components can contaminate that flow. If high-energy turbulent air enters the diffuser, pressure recovery is compromised and downforce falls off. Ride height also plays a huge role. Too high and the flow becomes disconnected from the underbody. Too low and the flow can stall or become turbulent. The peak performance of a given diffuser design is tied to a narrow window of ride height where the underbody flow remains attached and coherent. So what makes diffusers so powerful compared to other aero devices? Two reasons. One, efficiency. Because they operate on the entire width of the underbody and over a long chord length, diffusers can generate a large low-pressure region with relatively modest drag penalties. Two, integration. Diffusers link directly to the floor ahead of them and the wake behind. A well-designed diffuser not only recovers pressure efficiently, but also invigorates the underbody flow head, meaning the whole region under the car operates at lower pressure. This is why race car underbodies with effective diffusers produce downforce proportional to the square of speed, and why they are central to ground effect aerodynamics in modern motorsport. In Formula One, the diffuser is often cited as the single biggest downforce-producing device on the car. Its geometry is tightly regulated, but teams optimize its expansion ratio, strake placement, and interaction with floor flow to eke out massive downforce. In GT3 and endurance racing, diffusers are shaped and integrated with underfloor tunnels and strakes to balance stability and efficiency over a wider range of conditions. In all cases, the same principles apply: controlled expansion, pressure recovery, and resilient attached flow. So here's the real takeaway. A diffuser isn't just a shaped surface on the back of a car. It's a pressure management system, one that controls how the airflow beneath a car transitions back to ambient conditions. It uses expansion, controlled deceleration, and careful interaction with upstream and downstream flows to maintain the deepest low-pressure field possible. That's what makes diffusers so powerful and so central to modern aerodynamic design. Once you understand this pressure recovery mechanism, a whole range of other aerodynamic phenomena starts to make sense. And that's why, if you really want to understand how race cars stick to the track, you have to understand diffusers. Thanks for watching. If you enjoyed this deep dive and found it useful, consider liking the video and subscribing for more engineering-focused breakdowns. I'll see you in the next one.